Hi, I'm Todd Austin. I'm a professor at University of Michigan and also co-founder of Agita Labs, a company that makes TrustForge, a privacy-enhanced computation framework that performs zero trust data sharing. Today, I'm going to show a demo that uses TrustForge to determine if two spy satellites are going to collide with each other without showing the orbit of either satellite to the other. Let's take a look. So let's say we want to determine if two satellites are going to collide with each other, but we don't want to tell each other where our satellites are in space. All we want to reveal to each other is whether or not they will collide. And we can use privacy enhanced computation to do this without risk of revealing that information. This is a form of data sharing where the data sharing is occurring between adversaries, adversarial data sharing. Okay, so in the middle here, we've got a server running TrustForge. And this server is not trusted. We don't trust the operators of the server. We don't trust the programmers on this server. We don't trust the supply chain of the server. We only trust the TrustForge enclave, which is a hardware component deployed in Azure or AWS to do its job. And then my spy satellite will encrypt its orbital parameters and send it to this server, and then ask that it compare those orbital parameters to my adversary's spy satellite. Those are also encrypted and sent to the TrustForge server. TrustForge server then processes those orbital parameters, solving Kepler's equation and various other transcendental and trigonometric functions to determine if the two orbits potentially intersect. And in this case, these two orbits do intersect. In addition, it'll make sure that no one hacked into the server and changed the order of the computation of the program that was run. The data is always encrypted, so that can't be revealed. But someone could still hack into the server and for example, say, oh, you're not going to collide. And it uses its integrity checking mechanism to validate that the computation that was agreed upon was run with our inputs. If that occurs, then it will do what's called a safe data release, and it will release a single bit of information to both parties that are sharing as to whether or not there is a collision, a possibility of collision on those two orbits. And in this case, there was. Now, if someone were to hack into the server and change what the computation was, perhaps corrupt that computation. They can't see the data because it's always encrypted on this system, but they can change the order of the computation, change the program, like a supply chain attack. If that were to happen, then the integrity checking mechanisms of TrustForge would fail and the safe data release would not be possible and nobody would see any information about this computation. So using safe computation, we can very effectively implement a system which doesn't allow anyone to know anything except whether or not these spy satellites are going to hit in the case where the server runs the computation that we expected. That's really powerful. That power comes from a privacy enhancing technology, or a PET as it's called TrustForge. TrustForge is made by Agita Labs, a startup I'm associated with. And TrustForge is a small hardware enclave that's been deployed into Azure and AWS. You can use it today for your own privacy enhanced programming needs. It implements this encrypted computation that we saw in the previous slide, as well as safe data release. When the computation we agree upon runs, we can see the results of those computations. And the way you access it is just program in C++, Java, and C++, JavaScript, and Python, just normal DevOps enhanced through privacy enhanced implementation. And we've worked with our partners to do world-class security validation of this. And as of today, no vulnerabilities have been detected in this system as yet, under both formal verification as well as commercial red teaming. And this thing is really the Swiss Army knife of privacy enhanced computation. There are so many different programming domains that it is moving into, incredibly effective. In this video series, I'm just doing some really interesting program domains that have never been done before in the privacy world, like trying to figure out if spy satellites hit each other. All right, so let's take a look at the demo, the TrustForge demo on Orbital Collision Solver, trying to find out if two satellites are going to hit each other without revealing the orbits of those satellites. All right, let's take a look at this demo. First thing I'm going to do is I'm going to run my spy parameter, orbital parameters against my adversary's satellite. And since I set all this up, I'll just show you what it looks like. The larger orbit is my orbit, and the smaller orbit is my adversary's orbit. We're coplanar, so it's pretty easy for us to intersect if the path of our orbits cross each other. And so I will now, these orbital parameters have been encrypted. They'll be imported into the program, and then it'll do the computation and release that single bit analysis. So let's take a look at the first run. So I'm going to build my orbital collision detector. It's going to open a contract to access this data. And it said, okay, so it said, got the orbital trajectory information. It ran the solver to see if the orbits intersect, and then it attempted to decrypt that value intersecting with that single bit Boolean value. And then it said, yes, it was able to decrypt that. It says, yes, these orbits do intersect. So it was able to tell me that. So I got to fix that because I'm going to hit this other satellite. So what I would do is I would, do something like change my orbit. So what I'm going to do is I'm going to change my argument of periapsis. I'm going to sort of scoot this orbit around the planet here. And this is specifically my orbital change that I'm going to make. And then I'm going to ask the system to reevaluate that. And you can see in this case, we do not intersect anymore. So I'm going to go and change my argument of periapsis. I'm just changing these constants in the code that generates the encrypted values. And I'm going to rerun my test with those new orbits. And when I run the second orbit, it's going to say, when I decrypted that Boolean value, which it ran the computation that was expected, and I said, these orbits do not intersect. Fantastic. Now I know I'm not going to hit that other satellite. So success. We don't know anything about each other's orbits, but we do know we're not going to run into each other. Now, let's say there's some rogue programmer at the site that does the TrustForge computation. And that rogue programmer just, comes in here. We do all these heavy duty floating point calculations to see if there's an intersection. Then we come down here at the very end to see if D is greater than 0. And then we use this, what's called a data grant, which checks the computation that was used to compute intersecting. And if it matches the computation we expected using what's called a data flow hash, then it'll decrypt it. Well, I'm a rogue programmer. I'm just going to say, I don't want anybody to ever see any intersection. I'm going to just assign false here. And I'm going to rebuild the code. And I'm going to run the test. And it's going to indicate that there was no intersection, which is the result we got last time. But notice when we run this time, the decrypting primitive is looking at the data grant. The data grant says, I expected a particular piece of computation to be run to produce that Boolean value. The computation you ran is not the same because of my little supply chain attack there. I went in and changed that value. And so I cannot decrypt the result. It doesn't say false. It just says, I don't know what this value is. I cannot decrypt it. And in fact, I got to come back in here and change it back to the original code in order to get this to work again. If I change it back to the original code, then I can run the test and I get that same result that I got earlier, which is that there was no intersection. So this is a great system if you want to compare two pieces of information and render privacy preserving information off of that information you shared between adversaries. In this case, the information we've shared between adversaries are the orbits of their spy satellites, and the privacy preserving information that we're rendering is, do they intersect those orbits? Thank you so much. I hope you enjoyed the demo. If you'd like to learn more about me, please visit my LinkedIn page. if you'd like to learn more about secure computation technologies like TrustForge, like homomorphic encryption, like multi-party computation, go to this second link where you can see the slides from a class I taught last semester at University of Michigan, which covered that topic in detail. And if you'd like to learn more about TrustForge from Agita Labs and how that could potentially solve some of your privacy-oriented programming problems, please visit agitalabs.com. Thank you so much for your time. Take care.